Today we're in the lab and we'll be working on a new version of the Learning Tasmota PCB. Continuing where we left off in episode 7, we will complete the PCB design with easy EDA and send it off to China to be manufactured. Let's get started. In the previous episode, we created and completed an electrical schema in Easy EDA. In this episode, we will continue where we left off, which was at the beginning of the PCB layout phase. Today we will do the following. First, we will place all of the components on the PCB. Following this, we will manually route all of the connections or rat lines between the component pins using both sides of the board. We will then add silkscreen markings on both sides of the board for ease of use. Finally, we will create Gerber fabrication files and submit the design to JLC PCB in Shenzhen for manufacturing. We are under the gun as the Chinese New Year, the Year of the Ox, is upon us, and most of China's industrial engine will completely stop 2 weeks in February. We would like to have the PCBs completed and delivered to the Netherlands for our next episode in late February. Let's jump to the computer keyboard straight away and get started. We finished the last episode with a completed electrical schema in Easy EDA, which was verified. As opposed to editing the previous PCB layout, we will completely rebuild the PCB for the sake of learning and mastering. In the last episode, we were left at the beginning of the PCB layout phase with a board measuring 60 by 100 millimeters, along with a rat's nest of components. The component parts can be seen in yellow with white pin pads, as well as the blue rat lines between all of the pins. I always find this starting point a bit intimidating. As with all complicated things, we will divide and conquer all of this step by step. Before placing any of the components on the board, let's measure the drill hole locations. We will be using 2.5 millimeter metal screws from the PCB into the box, so I will make the hole size approximately 2.7 millimeters. The center point of the screw mounts in the corners of the black hobby box are approximately 5.75 millimeters from the outer edges of the corners. Doing some simple subtraction with a 60 by 100 millimeter board, we will determine the exact measurement positions for all 4 holes. The 4 drill hole points will use the key XY grid measurement values of 5.75, 54.25, and 94.25 millimeters. Let's do a precise final check of all of the hole locations of our board after having manually eyeballed their placement. With that done, we can now place all of the components on the board. All of the components will be placed in more or less the same position as the previous Learning Tasmota version 2 board. The only exception are the temperature and humidity sensors and the pull-up resistor components. In the interest of time, we will speed through the placement while I make some general comments. Component placement is strictly a manual process. With some of the parts, exact relative placement is important. For example, the WeWAS D1 Mini should be placed right on the edge of the board so that the micro USB connector can be easily plugged in with plenty of clearance. PCB holes should also have at least a couple of millimeters of space around them. The same goes with momentary push buttons for a human finger. There's a sense of craftsmanship and order that should be used when building PCBs, so using some of the Easy EDA tools to line up and space components is important. If you've ever built a PowerPoint presentation, you will find that all of the control tools in Easy EDA are very similar. We are now at the point where we need to route the connections between the component pins. The bluish lines again are called rat lines, and they act as a guide in terms of where connections need to be made. Routing seems to be one of those art forms where you never have a problem with unoffered advice. As a pure hobbyist, Here are what I understand to be the three most critical layout principles. First, do not use auto-router functions. The auto-router will try to make the connections in an automated manner. While I get that this may have not been the best way to route connections in the years past, there will also come a time, likely soon, where the use of heuristic and AI techniques will do this better than a human. Certainly better than a hobbyist like myself. We will continue routing this PCB manually, however. Second, never create connections with 90-degree angles. This is contrary to when designing an electrical logical circuit, which I made reference to in episode 7. With PCB layout, you should get in the habit of not using right angles, which is important especially for higher frequency designs. Third, make connections as short as possible and avoid using via holes between different layers of the board. A via is a connection in the form of a plated hole through the PCB. Vias are what allow connections to be made between different layers of the board. In our case, we're using a 2-layer board with traces on the front and the back of the board. In version 2 of the board, I ended up using several vias to unwind the rat's nest of rat lines. We will try to not use any vias in this version of the board while simplifying the routing of the board as well. There are many other techniques that are important, but for what we're doing here, these are the three most important points. My previous comment about not using the auto-router has some other reasons as well that are more about the enjoyment of the hobby. Routing can be mentally challenging. The routing of this board took me around 15 minutes, and I must say I enjoyed the mental concentration of trying to think 2 steps ahead of routing all of the connections. The end result is very gratifying. It's like a Sudoku puzzle, but with a practical application. If I had to route 2,000 connections on a board for a commercial product, I might not feel the same about routing all of these connections manually. At a certain point, it seems impossible to continue routing on the top side of the PCB, and we have to start routing from the other side. The red lines are the connections on the top of the PCB, while the blue ones are on the bottom. As you would expect, the last 20% of the connections are the hardest to route. One has to alternate between the top and the bottom of the board to find the easiest path, sometimes redoing connections. It may turn out that a long path around the outside of the board is necessary to avoid a via hole connection between layers. There are trade-offs that skilled professional PCB routers take into consideration. For this hobbyist project, however, the decisions are fairly straightforward. With all of the connections completed, we will start labeling the component connections. As this is a hobbyist board for learning and mastering, I perhaps have gone a little bit overboard with my markings. On the other hand, it makes things clear. For example, I mark every component connection linking back to the pin on the Wemos D1 Mini clear with both the D markings and the GPIO markings. I'm not placing markings on any of the LED current limiting resistors, however. This is something that should be left to the last minute when assembling the device. I'd like to get a set of resistors out from 100 to 470 ohms and test the brightness at 3.3 volts with each of the LED colors that I have on hand. I will add a starting resistor mapping recommendation on the back of the PCB just the same. The idea is to try to keep the relative brightness of each LED the same. Yes, I can be a perfectionist with the oddest things at times. And finally, we will create some text on the front and the back of the board. At a certain point, we can take a look at the rendered 3D view of the board. One can often see glaring, silly mistakes by doing this. In this case, I can see that I did not mark part of the board with the proper silk screens on the front and back. Let's go back and fix this. And with a couple of final finishing touches and fixes, we are done with designing the PCB. Now let's try to create Gerber fabrication files for this PCB. To do this, we will go to the File, Generate PCB Fabrication Files option. Before actually starting this task, the EDA software will verify that there are no missing connections or any other clearance errors. Given that we have reached this menu, Easy EDA did not find any errors. That's great news. At this point, we have two choices. We can either create a zip file of Gerber files, or we can simply have this work immediately transferred to JLC PCB for manufacturing. We will first create the Gerber files to see what they look like, but will then send this design to JLC PCB for prototype manufacturing. The Gerber files are output as a zip file, which contains around 10 files. These are ultimately text files for manufacturing the various layers of the board. Let's go back again and select the File, Generate PCB Fabrication Files option, but this time let's order at JLC PCB directly. After uploading the design into the JLC PCB portal, we are then asked several questions. All of the defaults are normally fine. The only one which I changed was the color of the PCB, which I kept red. From this point forward, we will go through the e-commerce checkout process. The cost of 10 boards is only $5. So what's the catch? How can this be so cheap? Well, this does not include shipping from China to wherever you are. I went with DHL Express standard shipping, which cost around $16 US to the Netherlands. Normally I would use some of the cheaper options, but we are so close to the Chinese New Year and all Chinese manufacturers will likely experience a surge before going away on holiday for 2 weeks. I did not want to take the risk that the shipping gets held up in China and we miss the time window. So my order is now placed, and I should see these delivered at my door in the Netherlands in about 7 to 10 working days if all goes well. Now it's time to wrap up. So what did we do today? Well, we finished up the design of the Learning Tasmota PCB version 3. We took the electrical schema into the PCB design phase, starting off by drilling holes and placing all of the components onto the newly sized board for our low-cost black hobby box. We then routed all of the component pins using both sides of the board and managed to do this without any via connections between both sides of the board. That was a bit challenging. The board was then finalized with some upgraded textural silk screen on both sides. 10 boards have been ordered from China at a total cost of around $2 per board delivered to my door in the Netherlands. These should arrive shortly. In the next episode, we will assemble a board and make sure that everything works as expected with the proper measurements. I have placed links to the black hobby box and the Easy EDA tool in the notes below. Thank you for joining me today in this video. If you found this video useful or interesting, please click the like button below. Please also consider subscribing to the channel to get a front row seat when I release new videos. This is Mark at marktroyer.tech signing off.